In this lesson, I will be showing you the manual computations on how to analyze and design strap footings. Strap footings are a kind of technique in which we combine footings by using what we call a strap beam. So it's also a kind of combined footing, but instead of combining the footing pads, we use this strap beam. We usually do this when one of the footings is near the boundary line or the boundary of the lot, and we cannot spread that footing out towards that lot area. So we have several design considerations when designing strap footings. First is we want the contact pressure to be uniform. The external footing can be designed as a wall footing because of the presence of this strap, so it can be designed like a wall footing. And another consideration is that the interior footing is isolated with a large edge column because of the strap. And that interior footing is commonly designed to be a square footing. That's why the width and the length would be equal. Now let's look at an example. So here is an example. We have a footing with several dead loads and live loads on their columns. We have two footings and we will combine them using a strap beam. The first step when designing a strap beam is we have to assume one dimension for the first footing. Some solutions will give you the width of the footing. In this case, in my example, what I'll do is I will be assuming the length of the footing by using what we call the eccentricity of the reaction below the first footing. So if I assume that this eccentricity is 1 meter, I would be able to get the length of footing 1. Because, as you can see, this eccentricity up to this edge, that would be E plus the dimension of the column over 2. And that would be equal to the length of footing 1 divided by 2. Therefore, substituting our assumption for the eccentricity to be 1 meter, we will get the value of the length of footing 1. So, footing 1 would have a length of 2.25 meters. That would be the assumption for the length of footing 1. After that, we can now solve for the reaction. We solve for the reactions R1 first by getting the moment at the centroid of footing 2. So let's write that out by summing up the moment at the centroid of footing 2. This should be equal to 0. So we have P sub 1 times the spacing between columns, which is 4.7 meters, minus R sub 1 times 4.7 minus the assumed eccentricity, which is 1 meter. This should be equal to 0. Now, P sub 1 is the service load for column 1. And the service load for column 1, that would be 400 plus 220. Doing this, we would be able to get the reaction below footing 1. So the reaction below footing 1 is 787.568 kilonewtons. Next, by summing up the vertical forces, we can get the value of R2. So we have T1 and T2. They are downward forces, plus R1 and R2, upward forces. They must be equal to 0. This came from the equation, the sum of vertical forces must be equal to 0. So substituting the values, this is what we get. R sub 2 is equal to 882.432 kilonewtons. Now that we have the reactions below the bases of each footing, we can now determine the required footing areas and dimensions. The areas of the footing will be based on the allowable soil-bearing capacity. It is governed by this equation. Q sub K is the contact pressure, and this must be always less than the soil-bearing capacity. Notice that the soil-bearing capacity given is already a net value. In other words, the weight of the footing slab and soil is already subtracted here. So we don't need to worry about that. So for footing 1, let's continue. For footing 1, the contact pressure would be the reaction below putting 1, which is 787.568, divided by the area of the putting 1, which is B sub 1 times the length of the putting 1 is 2.25 meters, and that must be less than 130 kilopascals. This gives us a condition for B sub 1 which should be greater than or equal to 2.693 meters. So I can say B sub 1, we can make it 2.70 meters. We follow a similar procedure for putting 2. That is, the reaction is 882.432, and we divide it by the area of the putting 2, which is B sub 2 squared, since we will be designing the interior putting as a square putting. This should be less than or equal to the allowable soil bearing capacity, 130. Solving for this, we get B sub 2 must be greater than 2.605 meters. So we can say B sub 2 is 2.61 meters. Now that we have the dimensions of the putting, we can now proceed in determining the adequate thickness for each putting pad. And in order to do that, we must first get the ultimate load pressures or the ultimate load combination. So the ultimate load for column 1, PU sub 1, since the given are dead load and live load, we multiply them with the load factors 1.2 and 1.6. The ultimate load for column 1 would be 832 kilonewtons. Similarly, the ultimate load for column 2 is 1.2 times 600 plus 1.6 times its live load of 450 kilonewtons. This will give us an ultimate load of 1,440 kilonewtons. Now, to get the ultimate soil pressure, this would be equal to the sum of the loads divided by the total area of the putting pad. So this is 832 plus 1,440 divided by 2.70 by 2.25 plus 2.61 squared. So the ultimate pressure below the putting pads, that would be equal to 176.30 kilopascals. RU1 and RU2 can now be computed. These are the resultants of the pressure below each putting by multiplying Q sub U with the corresponding base areas of each putting. Now, to determine the thickness of putting 1, again, we will consider it like a wall footing, and we will be checking the one-way shear capacity of footing 1. The critical section for the one-way shear is here. It is at a distance D from the strap beam. So the strap beam is like the wall, and we will get a distance D from that. That's the critical section for one-way shear. Now, in order to compute V sub U, or the shear demand, that would be Q sub U times the area of the shaded region. V sub U is therefore equal to 176.3 per 0.30 times the area, which is 2.25 times 1.1 minus the effective depth D. Now, the shear capacity of concrete for one-way shear according to the code is Phi times 1 over 6 square root of F prime C BWD. Substituting the values, we get Phi B sub N is 0.75 times 1 over 6 times the square root of F prime C, which is 28 megapascals, and times 2.25 times D, and we multiply this value by 1,000 as a conversion factor to get a value in kilonewtons. Now, from the design condition that the demand must be less than the capacity, we can solve for the value of D. And D, in this case, must be a value greater than 0.231 meters. The thickness, therefore, is a value that is greater than 231 millimeters plus a concrete cover of 75 millimeters plus 1/2 the diameter of the main bars of the reinforcement. So T is a value that must be greater than 316 millimeters. So we can say that the thickness that we can adopt for putting 1 is 320 millimeters. Next is we can design the transverse bars for footing 1. To do that, we need to get the critical section for the moment. And this would be the critical section for the moment of the transverse bars in footing 1. It is directly at the edge of the strap beam. So in order to compute for the moment, that would be 1/2 Q sub UB times L squared for the moment arm. So we compute for the moment, that's 1/2. Q sub U is 176.30. B is the width shown here, which is 2.25, and L squared, or L is the moment, the length of the cantilever, which is 1.1 meters. So we multiply this by 1.1 squared to get a moment, which is 239.988 kilonewton meter. We proceed with standard reinforced concrete design. First, I will get R sub n, which is 239.988 times 10 raised to 6 to convert it into Newton millimeters. We divide it by 0.9 times the width times a depth of 235 squared. Now, this depth is the effective depth, 235. It came from, because we know that the thickness is 320, we subtract 75 and half of the bar diameter. So the effective depth is 235. Our sub n here would be 2.146 megapascals. Getting the required steel ratio, we use the equation 0.85 times F prime C over Fy multiplied by 1 minus the square root of 1 minus twice R sub n over 0.85 F prime C. Now, I like to express my steel ratios in percentages, so I will put times 100% here. Solving for the required steel ratio, we get the following, which is 0.805%. This is obviously greater than the raw minimum or the minimum steel ratio required. The minimum steel ratio required can be solved by dividing 1.4 with Fy, which is 280. We will use that to determine our steel area. So we have 0.00805 times the width to 250 times the depth of 235. This will give us a required steel area of 4,256.44 millimeters squared. And by dividing that value by the area of a single bar, we get 13.55, or say 14 pieces of 20 millimeter bars. Next step is, since the footing 1 is a kind of a wall footing, if we won't be designing the longitudinal bars using the moment or in terms of flexure, but rather we will design it, or we will be providing temperature control or shrinkage control bars for footing 1. And the equation for that is we multiply 0.002 times the width, for in this case that would be 2.7 meters, times the thickness. So A sub S is 0.002, the width is 2.7 meters or 2,700 millimeters, and the thickness is 320 millimeters. This gives us a required area of 1,728 square millimeters. And again, dividing that by the area of 1 bar, we get 5.5, or say N is 6 pieces for the temperature or shrinkage reinforcement. Now let's move on to footing number 2. First, we check the one-way shear in the X direction. As you can see, we will be following a similar procedure as what we did with footing 1. So V sub U here would be Q sub U, or 176.30, multiplied by the shaded area, and the width of footing 2 is 2.61 meters. So this is times 2.61 times 1.055 minus D. And the capacity of the concrete for one-way shear, this would be 0.75 times 1 over 6 times square root of 28 times 2.61 times D, and we multiply again by 1,000 for conversion into kilonewtons. From the condition that VU must be less than or equal to V sub N, we can determine a value for D which must be greater than 0.222 meters. The thickness therefore should be a value that is greater than 222 millimeters plus 75 plus 1/2 the diameter, or it should be greater than 307 millimeters. We will take note of this first, and let's go back there. We will go back here after we check the one-way shear in the other direction. So we also need to check the one-way shear for putting 2 in the other direction. So here, B sub U would be 176.30 times 2.61 times 1.105 minus D. The shear capacity is 0.75 times 1/6 times square root of 28 times 2.61 times D times 1000. And following our procedure, we can get a value for D which must be greater than 233 millimeters. Now, the thickness should be a value greater than 233 millimeters plus 75 plus dB plus dB over 2, because in this direction, the bar layers would be above the transverse direction. That's why we add an additional dB. So in this direction, the thickness should be greater than 338 millimeters. Recalling our required thickness in the x direction, this is 307. Here, the required is 338. So this thickness governs our design. Therefore, we can say, or we can adopt a thickness of 340 millimeters. Note, however, that this is not a wall footing, but rather a footing with a large edge column. So, we also need to check the two-way shear for footing 2. And for the two-way shear in footing 2, the critical section will be this section. So, the perimeter, the critical perimeter for two-way shear would be twice of 1.505 plus D over 2 plus 0.5 plus D. And the area, that would be 1.505 plus D over 2 times 0.5 plus D. V sub U will now be solved by multiplying Q sub U times the area of the footing minus A sub O. And phi V sub N would be equal to phi times 1/3 square root of F prime C V sub O D. I will leave this part as an exercise for the viewer to check that the thickness here will not be governing our design. One-way shear in the y direction is our critical shear in this problem. So the thickness that we will adapt is 340 millimeters. Next is we will be designing the transverse bars for footing 2. First, we get the required moment. So this would be 1/2 Q sub UB times L squared. Substituting the values, we get the following. So we have 1/2 times 176.3 times B, which is 2.61. So B here should be 2.61 times 1.055 squared. So the moment for footing 2, for the flexural reinforcements of footing 2 in this direction, that would be 256.075 kilonewton meter. Doing the steps that we did previously, like in the footing 1, we get R sub N is 256.075 times 10 raised to 6 divided by 0.9 times 2610 times an effective depth of 255 square. And note that this effective depth is because we have 340 as our thickness minus 75 minus dB over 2. So the effective depth is 255. R sub N now is solved, so we can calculate it as 1677 megapascals. The required steel ratio is now determined using our equation, which gives us a required steel ratio of 0.622%. Again, this is greater than the minimum required, which is usually equal to 1.4 over 280 or 0.5%. Using that steel ratio, we can get the required steel area, which is equal to 4,139.721 millimeters squared. And again, in order to determine the number of bars required, we divide that by the area of a single bar, which is pi over 4 times 20 squared. So we say that the number of bars required in the transverse direction is 14 pieces of 20 millimeter bars. Next is we design the longitudinal bars for putting 2. The design for this one would be governed by this cantilevered portion at the right side of the footing. Again, the width of the footing is 2.61 meters. Doing the necessary steps, first is we get the moment. M sub u now is equal to 276.143 kilonewton meter. R sub n would be 2.129 megapascals, and the required steel ratio, you would be solving it to be equal to 0.798%. The required steel area is 4,894.533 square millimeters, which translates to a number of bar of 15.58, or we can say N is 16 pieces for the number of bars in the longitudinal direction. For the design of the strap beam, we have several things that we must consider. Usually, the width of the strap beam should be larger than the larger column size by 100 to 200 millimeters. This is so that we can place the bars at the sides of the column. The design moment and shear will usually occur at the edge of one of the footing pads. The depth of the strap is based on minimum shear reinforcement. So when we provide minimum shear reinforcement, this usually happens when the shear capacity is greater than V sub u, but V sub u is about greater than 1/2 of V sub n, where the shear capacity is based on the beam shear capacity, and the required shear reinforcement would be based on this equation. A sub B is equal to BWS over 3FY, where S is the minimum or the lesser of D over 2 or 600 millimeters. Now let's design the strap beam. First is we have to get the ultimate moments and shear. Now, we know that the ultimate pressure under each footing is 176.30 kilopascals. We can get the resultants by multiplying this Q sub u by the area of the footings. R sub u1 is therefore equal to 1071.023 kilonewtons, and R sub u2 is equal to 1200.973 kilonewtons. The critical sections that we will check for the ultimate moment and shear are these sections. The shear will be equal to negative 832 plus R sub u1 1071.023. This is the shear coming from the left side, which is 239.023 kilonewtons. That would be similar to the shear if we take the sum of the forces in the right side. For the moment at the left side, that would be negative 832 times this distance, that would be 2 meters, and this distance, that would be L over 2, so that should be 1.125 meters. So again, taking the moments, we have negative 832 times 2 plus 1071.023 times 1.125. M sub u therefore is negative 459.099 kilonewton meter. This is the moment at the edge of footing 1. Now, getting the moment of the edge of footing 2, we do a similar procedure. So we have M sub u is equal to negative 1440 times a moment arm. The moment arm is 1.305 for both PU2 and RU2. So what we find out is that the moment near footing 2 is equal to negative 311.932 kilonewton meters. So in other words, M sub u for footing 1 will govern. This would now be the design, shear, and moments for the strap beam. The required depth of the strap beam will be based on the shear force. Recall that the shear force is equal to 239 0.023 kilonewtons. Now, from the condition that VU must be less than or equal to VBN, we can now solve for the depth. So, VU, 239.023. We set it equal to VBN, which is 0.75 times 1 over 6 times square root of 28 times the strap width, which is 0.5 meters, times the depth, and we multiply this value by 1000 to convert to kilonewtons. From here, we get a depth that should be greater than or equal to 723 millimeters. The thickness, therefore, is the value which is equal to 723 plus 20 over 2 plus, plus 20 over 2 plus the stirrup diameter. In this case, let's say that the stirrup diameter is 12 millimeters plus the concrete cover of 75. So here is dB over 2, ds stirrup, and 75 is the concrete cover. So now we say that the thickness must be greater than or equal to 820 millimeters. Let's just adapt the thickness to be 820 millimeters. If we do this, we need to provide the minimum area of stirrups. So the minimum area of stirrups, A sub B, is BW times S over 3 times Fy. BW is the strap width, which is 500. S is the lesser of D over 2, or 600. So 723 divided by 2, that would be 361 divided by 3 times 280. So the minimum stirrup area is now equal to 214.881 millimeters squared. We can divide this by the area of a single leg of our stirrup, which gives us 1.8 or 1.9. So we say 2 legs for our stirrup is okay. And remember, the spacing is 361, so we can say that the spacing is about 360 millimeters. Next is we design the flexural reinforcement for the strap beam using an effective depth of 723 millimeters. We can get R sub n using our beam formula. So the moment is 459.099 times 10 raised to 6. We divide this by 0.9 times the width times the effective depth of 723. So R sub n is 1.952 megapascals. The required ratio is determined using our previous formula. So we have 0.85 times the concrete strength divided by the steel strength. We multiply this by the quantity 1 minus the square root of twice R sub n divided by 0.85 times the concrete strength, which gives us a required steel area of 0.728%. Again, this would be greater than rho mean of 0.5%. So the area of steel required is now calculated by multiplying the steel ratio with the effective area, and N is computed by dividing that steel area with the area of 1 bar. So we say N is 9 pieces. We have now designed both the puttings and the strap, so we can summarize our design. Here are the sizes. For putting 1, it's a 2.25 by 2.7 putting. For putting 2, it's a square putting with dimensions 2.61 meters. The width of the strap is actually given in the problem is 500 millimeters. The thickness for putting 1 is 320, while the thickness for putting 2 is 340. The strap will have a depth of a total height of 820 millimeters. The bars are shown here. The transverse bars for putting 1 is 14 pieces of 20 millimeters. And we have the temperature bars for putting 1, 6 pieces of 20 millimeters. Now, for putting 2, since this is a square putting, it is customary to use the same number of bars in both directions. So we solve here 16 pieces in the longitudinal direction and 14 in the transverse direction. Sometimes we just provide the same number of bars, so we adapt 16 pieces in both directions. And also we have our stirrups spaced at 360 millimeters. Now under the beam, So since the beam was designed for a negative moment, we have the top bars, which are 9 pieces of 20 millimeter diameter. The bottom bars would be the placement bars. That's where you tie the stirrups and you use it to anchor the top bars. That's usually taken to be at least 2 pieces, or the number of top bars divided by 2. In this case, it's 9 divided by 2 is 4.5. So we can say, let's provide 5 pieces for the bottom bars of the strap beam. So that's an example of the manual design of a strap coating.
Like mo yung video kung ayos. Pag hindi, pag mo i-dislike, leave ka ng comment kung bakit, ha? Sige na, subscribe.